Hello, so I'm back. Flo is running around tabs. So let's continue because we had a little bit of, we're a little bit late. We're gonna listen to Philippe Arteau now. He's a security researcher working for GoSecure. His research is focused on web application security. His past work experience includes pen testing, secure code review, and software development. He is the author of a widely used Java static analysis tool, OWASP, Find Security Bugs. He is also a contributor to the static analysis tool for .NET called Security Code Scan. He built many plugins for Burp and Zap proxy tools, including Retire.js, Reissue Request Scripter, CSP Auditor, and many others. Philippe has presented at several conferences, including Black Hat Arsenal, Sector, AppSec USA, ATL SecCon, NorthSec, and 44Con. He's also a very invested volunteer for NorthSec and for the CTF. So let's give a good round of applause to Philippe Arteau, who's going to talk about Unicode vulnerabilities that could bit or bite you.
Hi, everyone. So hi, everyone on Twitch or seeing the stream later. So I'm going to talk today about security related to Unicode or security risk implication with Unicode usage in a web application or system in general. So without further ado, I'm going to start my slides. So as you have seen, the title of my presentation has a fun, but also a Unicode character that is also aimed at testing a system from conferences. So far, NorthSec is supporting Unicode greatly. So that's pretty good. We'll see later what these type of characters are about. The main topic of this presentation is transformation that are standard from the Unicode that can have a security issue. So first, we're going to go through a basic history of encoding, just to see what solution Unicode is trying to solve, or what problem is trying to solve. Normalization and case modification will be transformation that can have security impact in your code or library that you're using. We're going to see also that Unicode can be used by pen tester or bug bounty hunter to bypass WAF or any type of filter. We have also two other sections that are maybe as important but less technical that I'm going to go quickly through. So homograph attack will be usage of special character in Unicode to do basically to fool user with Unicode domain. And data integrity is also an important topic related to loss or partial loss of data. So who am I? I already got a great introduction about me a moment ago, so I'm going to go quickly. So I'm working for GoSecure as a security researcher in application security. I'm also a volunteer at NorthSec, so I'm often doing CTF changes depending on the year, but I'm also helping with the website of NorthSec. So before we start, I'm going to go through a basic introduction of encoding. The first type of encoding that, not necessarily the first one, but one of the early one was ASCII that emerged in the early 60s. And the way ASCII worked, it was pretty primitive, but it was pretty simple. Every byte was one character. So when you need to write a text, also think about text file, but maybe a message that you need to send or anything that you need to store, in ASCII, one byte equal one character. And the way the different bytes are attributed, because one byte can have value from 0 to 255. So the first 32 values are a control character that would be used to basically interact with maybe the computer or other programs. So think about null character, bell for the console, backspace, and the file, these type of characters. So these are non-printable characters. Then we'll have a standard character set, so Latin character, So every character from the alphabet, uppercase, lowercase, but also numeric values and some punctuation. Then we'll have the extended character set, and those are aimed at covering special characters in text. So if you are writing maybe a French text or a Spanish text, you'll have accented character in your text. And the idea is that all accent characters will be stored in this section. The thing is that we cannot store all accent character of every language, so we'll need to do some choice. And with this limitation, system around the 60s and 70s have implemented different extended char sets. And these were called code page. Code page will be basically variation of the second half of the assigned byte. So any character from 128 to 256 will be assigned a different code page. So IBM PC would have by default a code page, but maybe a Russian computer that is writing text could use some code page to write a text with Cyrillic character to be able to write Russian. But at the same time, if you want to write a text in Greek, you can use code page 737. And the idea is that you can have multiple files with multiple code page, and you can switch between those. But with this type of implementation, there's going to be a multiple problem. And one of the problem is, what if I want to transfer a file from one system to another? So now we're going to have maybe a system that has code page 437. So DOS Latin, the basic, the default one on IBM PC. And if the same file is transferred maybe over the network or over a diskette, then on a Russian computer that has maybe a Cyrillic default encoding, then suddenly accent character can be translated to different characters. So suddenly we're losing information, and the message is transformed. So that's one issue, but also we cannot have at the same time in one text maybe a French description with quotation in Spanish or quotation in Cyrillic, because it would be hard to switch or in a text file from one code page to another. So there are some big limitations to using ASCII. So as soon as we're doing communication or exchanging file, the more we exchange file, the more these limitations can be problematic. So the big solution for this, there were multiple IDs, but the main one that is still used today is Unicode. So Unicode is a standard that defines both characters and encoding of characters. So the first component is Unicode code points. And code points are uniquely indexed characters. So every character in every language will have a unique code points. So the idea is that in a single standard, we're going to index every character of every language, including a symbol, measuring unit, and even language that are not even used anymore, like hieroglyph. And for example, if we look at the third character, the green one, which is a Japanese character for water, this 6C34, this is not necessarily the representation in byte of this character. This is the index of this character in Unicode. So it's a unique number for the concept of this character. Code points are not defining the way characters are encoded, but there will be multiple encoded that are defined by Unicode. And one of them, which is the most popular one, is Unicode transformation format 8 for 8-bit. So the interesting element with UTF-8 compared to ASCII is that now suddenly we have a variable length encoding. So we cannot think anymore as one character is 1 byte every time. It will be in some cases. So for all ASCII or Latin character, they will be equivalent to the ASCII character. But any character that has a punctuation, accent, or any other language other than English will be encoded differently. So yeah, and the way we know the number of bytes used by each character, the number of bits at the beginning of the first byte will define. So for example, for 2 bytes, we'll have 110 extra until to a maximum of 6 bytes with 61 followed by 0. So as I mentioned, UTF-8 is the most popular. The chance that you see auto encoding is pretty rare. At the moment, web server, even desktop are mainly using UTF-8. But we still need to keep in mind that there can be some other encoding, because Windows for a long time was by default using ISO 8859. Even early version of Windows 10 were using this encoding, which is basically ASCII with a code page that support character that are have accent for French, Spanish, and a few other language. But slowly, even now, Windows is switching to a default of UTF-8. I think it's in the past 2 years that they are starting the switch for both the system and console of Windows. So what can happen if you there is no encoding declared and you assume that it's UTF-8? So maybe you have a user that is using Windows that is writing a text, plain text file. So it can be, for example, a CSV. CSV doesn't have declare encoding by the way it's defined. So your user is saving with its default text editor in ISO 8859. But if your system, so your web application, is opening this file and thinking it's UTF-8, you will have some character that will not be recognized because it's not encoded the way you think. So that was the long introduction for basic concept of where Unicode came from and what the problem is it's solving. Now we know that Unicode is encoding all character from every language. The thing is that the same character, or same visual representation can be encoded in different way with different Unicode characters. So for example, I've at the top right, you can see a few examples. So the capital C with Sigilla can be both written with a single character, but also with a capital C with a combining character that will include a Sigilla. A bit like the character on my title slide, which has a combining character, which is I on top of any character. And the idea with normalization is we're going to try to compare a Unicode string and see if they are actually have the same meaning or are equivalent. So we'll have NFC normalization and NFC KC, sorry, normalization. And there are actually 2 others that are really similar to those 2. So I've simplified a bit for this presentation. And those normalization will happen in multiple use case in your web application or library. So sometime library will transform your input with and try to normalize them, maybe because they are building a URL and they are trying to make sure the host name will be valid or DNS friendly. Sometime user path, when file are read, are normalized to make sure special character will be properly handled when we request system API. Sometimes just to some transformation outside to username or this type of data. It's also being used sometimes to generate slug because the NFKC specifically normalization will convert many characters to ASCII character. So sometimes people will use it to basically transform special character to ASCII-only string. In practice, this is not intended for this. Unicode doesn't clearly document why in which use case it's safe to use normalization, but basically it's used in multiple cases to compare string or simplify the string to comparable format. So I already mentioned there is NFC and NFKC. So the first C means canonical, and because compatibility couldn't be just NFC, they've added a K for compatibility. So it's a bit confusing. But what you need to remember is that NFC is a strict comparison of equivalence that will have, for example, will match the CCZilla as a character or the decomposed version of it. But the compatibility mode will include, it's a much more flexible comparison. So for example, if we normalize the scripted H, it will be equal. It would be as a result capital H. So it will be equivalent if we compare them to the ASCII or Latin H. Same for fraction; they will be decomposed. Exponent will be also decomposed. Many measuring units will be converted to ASCII ASCII character. Also, there's a ton of characters that are just circle around a character that will become decomposed to just the ASCII version of it. So where is the security risk? So far, I've done a big introduction on Unicode. I've started to see that many API do normalization to help potentially the developer or the user to have valid input. It can have some side effect, and the first one, the host split attack, which was presented at Black Hat late the summer last year. So basically, we're going to have some character that will be converted to equivalent ASCII character and can create issue in URL or file path. And we have this very visual example where we're going to do maybe a redirection, maybe for OAuth 2, and we're validating that, okay, the domain to which we're redirecting are only subdomain for Microsoft.com. The thing is, the attacker will use a Unicode character here, account hub. So this is the A/C is a single Unicode character. But because in the location header, browser used to normalize this character to A/C, so all in ASCII. So browser were doing this probably to help developer have valid URL. So they were doing a normalization pass. So this is not an issue that was on the server side, but implicitly the browser were converting URL to this. So in the end, if we're redirecting OAuth 2 with secret token, suddenly we can exfiltrate potentially interesting values to our own domain that we control, because we have just break the URL and we're controlling those things. So a few other example with @symbol, question mark, and slash. Some other example in compatibility mode. So I hope I didn't miss too much. So right after showing a couple of examples of normalization, I just wanted to show a quick tool I've built. It's an interactive list of characters that can have interesting security implications. So if you think some application is doing some normalization on some string or URL, you can look at character, for example, this exponent A. I'm going to zoom into this, if that's possible. And basically, it's explaining you, okay, this character 0AA code point is converted to ASCII A, so 61. And this is the way it's being encoded. In different language, it will look like this. And you can also, there's a few options. So you can decide to hide code section per language. Also, some character transformation will not be effective in some language. And you can filter if you only want to look at NFC, which is the canonical. So this is the most strict normalization, but as you can see, NFKC will have a bunch of characters to choose from if you need to encode some character to do some bypass something. And the search feature can be used to if you need what character you want to use, you can search, for example, K, which Unicode character can potentially be converted in transit by some library or some function to ASCII character. So in some cases, it will not only be ASCII character, so sometimes there will be an apostrophe after the letter, but the idea is all those Unicode characters can be translated to ASCII if the specific transformation is applied. So that was for the quick example. I'll paste the link in Twitch right after this presentation. So if you want to play with it and search for characters, and also to test the application in the context of pen tests or even bug bounty. So general recommendation, if you are doing security check, make sure you do normalization before there's any security check. Because if you do a validation and, for example, look for a blacklist, there's no the keyword X, but there is, after the security check, a normalization that could generate the keyword X. You can have a bypass. Review the library you're using, especially if you have a critical application that is doing some validation on host name or stuff like that. Maybe the HTTP library you're using or the network library could do some normalization and you don't know about it. So you can test it with the character I'm providing in the list. So again, prefer general security rule of thumbs, prefer whitelist over blacklist if it's possible. And do strict validation at the source. So I'm going to jump to case modification, which is pretty similar to normalization. You're going to see. So a case modification will be every time we do two uppercase or two lowercase transformation. So Unicode define the behavior for every character, what should be the result for the uppercase and lowercase transformation. So for this reason, almost all language will have the same behavior. I've noticed that Go and C# do have a more limited a subset of characters that can become ASCII. So it's there are a few that are not covered in both in Go and C#. But aside from that, Ruby, Java, PHP, most of them have the same behavior as defined in the Unicode standard. Also, not all characters will have variants. So if you apply uppercase to some special characters, sometimes they will not have any variation. But many characters will have redirect to the same character. So, for example, we're going to see an example in a moment, but the Kelvin degree, so for the temperature, the Kelvin symbol, if you apply the lowercase transformation, it will become lowercase k, like the ASCII Latin character. So if we apply uppercase transformation to lowercase a, it's pretty obvious, no surprise, it becomes capital A. But it's interesting to know that there's a few other characters which are also on the same application that I just presented that will become ASCII characters. So this German B will become SS, so capital S. And this is because it's part of the German language. This is the way the language works. There's not the capital B like this one doesn't exist. It's written with two S. Same with this FI character that is a ligature of F and I. It becomes capital F and capital I, which is, if you compare it to the string FI, would be equal. Lowercase will have completely different character that will have this behavior. So character that have impact on uppercase transformation does necessarily have the same repercussion with lowercase transformation. But K will work, so if we do a lowercase of the 24 to A character, which is the Kelvin degree symbol, it will become 6B, which is ASCII key. So if you're comparing host, and one of your hosts could be a Facebook, IKEA, or VK, I don't know, you can possibly put 21 to A if you're trying to bypass the filter. There's also this Turkish character that can become lowercase I along with some apostrophe. So there should be a dash right above the I, but basically it's a dotless I, but with a dot on top of it. So PowerPoint is not rendering properly, but so it's not exactly ASCII, but sometimes it could be enough if the second part is later truncated or removed. So again, potential issue will be similar to a normalization. So if you're doing a critical security check on strings and you have done 2 uppercase or 2 lowercase on your value before doing the security check, this can cause some issues. It can be used also to bypass WAF or filters, so similar to normalization. So quick example, so if we're maybe looking for is the current role or the current user equal to admin, we might not be in the application able to register an admin user, but we might be able to register ADM with dotless I M, and this character, once the uppercase transformation will be applied, will be equal to this admin in all in ASCII characters. So another example, this is a Java code of a class doing host validation in TLS communication. So here we have 2 variables, name and templates. So name will be the host to which we're connecting, and template will be the host name which the library has extracted from a certificate. But because 2 lowercase is applied, then we could have a malicious certificate that would have Kelvin K, for example, in host name, and the Kelvin degree would be transposed to a lowercase k in this case, and could be used to bypass this host verification. We have this also this recent penalty in Django, where this is a password reset functionality, where basically the email was doing a weak comparison with, I think, lowercase, and in the end, the problem here is that first there's a weakness in the comparison of the email with the database that is storing the user, but it's sending an email to the original email in the form that was submit. And because of this, we could have, we're trying to impersonate maybe superadmin, and we're going to register a superadmin account with I that is .si. Here, the feasibility and the actual exploitability might not be possible if we don't manage to have a SMTP server that receives this email. So I'm not 100% sure it can be possible on a real application, but this is a vulnerability that was patched in the Django. And the fix was, they changed the comparison, but it's not this that is doing the completely mitigating the problem here. What they have done is that instead they are extracting the email again from the database from this user to make sure they are using an email that they are trusting in the first place, so a value from the database. So mitigation similar to normalization. So, but here in most language and library, when they are doing security critical check, they will have a custom function that are making sure that lowercase are only applied to ASCII character. This is something I've seen in the GDK, for example, in Java, and a few other libraries. In C#, they have a save function that is 2 lowercase invariant So if you want to do a case insensible check, you can use this function. It would be safe. Okay, so I'm I'm told that I'm almost done with time, so I'm going to quickly go through the encoding bypass for WAF, but I'm going to have to skip the small two section for the data integrity and the Unicode visual, which was just only a couple of slides. So WAF will be a system in between your client and your web application or your system. And the idea is that we'll encode in a way so that the firewall that is looking for specific string will not see the malicious pattern and reach the web application. So UTF-8 is pretty common, but Unicode is defining a few other encoding that might be supported on your system. One interesting one is UTF-16. UTF-16 has a system of byte order mark, meaning that even if your default encoding is UTF-8, if you define in your text file, maybe XML file, byte order mark for UTF-16, automatically the XML parser will switch to UTF-16. So this can be useful if you have something in between that is looking for malicious XML payload. You can encode it with in UTF-16, both little endian or big endian. So a quick example here of how this file would look. So this is a XML document encoded in UTF-16. So we can see there are some byte order mark at the beginning, and every character is taking 2 bytes. In practice, if you open this on your editor, or the way your application would see it, it would be as a regular XML document. XML also has another option, specifically if it's XML documents. In XML, you can define in the first declaration node the encoding, and from this, it will switch to this encoding. So even if your parser is being specified, use this encoding, it can be switched also this way. The screenshot is showing an interesting parser, which is a libxml2 in C. And what's interesting is that the encoding is switching right after the attribute instead of the end of tags, the first declaration tag. So this is an interesting behavior. But in the end, it's going to be the same principle. We just want to bypass maybe we have some malicious path that we're using, or malicious method that we're using in our XML payload to do an XXC or some type of RCE. But because we're encoding it in UTF-16, we might be able to bypass some filters. So I need to quickly mention that while UTF-16 can be useful resources for bypassing filter, there might be some easier ways with XML entities, double encoding, non-printable character in the case of bypassing XSS, for example, because browser often truncate non-printable character. But yeah, I just need to mention it. It's maybe a bit out of scope, but I need to mention it because it's probably an easier avenue in most cases. And the last element I want to show for implication of Unicode in to bypass filter, there is a common bypass for XSS filter in .NET. So this is less an actual thing because .NET Core has dropped its XSS filter. But basically, in most .NET application will use SQL Server. And SQL Server, or maybe the client library, I'm not sure which component is doing normalization, but if you're having a column that is nvarchar, depending of the collation, so the default encoding of your database, character might be converted to ASCII character. So in this case, we're inserting an image source, but with the character FF1C. But the way it will be stored, it will be the ASCII character. So in practice, we'll have our store XSS, and it will render as on the right. So I'll have to skip the 2 last section, which are pretty quick. It was just a quick example of Unicode attacks. So for example, here N with underscore with a small dot counter, few recommendation, and make sure if you are doing conversion that because in some language character will be truncated or replaced with unknown one. So make sure if you're migrating or doing backups that character are properly saved. So, and I'll be sharing the link to the slides. So if you want to see the last couple of slides or see the resource that I've mentioned along the way, these will be published on this URL. So I'll paste it right after on the Twitch streams. But yeah, or you can visit it right now. So it's at gosecure.github.io/presentation if you want to get the slides.
Welcome back. So we have one question here. It says, does this allow, sorry, I'm getting a little bit tired. Does this also work in certificates? Would it be possible to spoof a valid certificate by using Unicode characters like Kelvin K, for example?
Yes, okay. So basically the code that I've showed was an example of a Unicode vulnerability. So this is a specific vulnerability of a specific language, I would say. This is currently patched, but the vulnerability is not officially released. So that's why I didn't put a CVE or anything specific. But the reason it's not that critical to show it in this presentation is that in order to do full TLS interception, you will need more than just bypassing host name verification. So, for example, if you want to man in the middle Android application or basically any type of client, you need to have a certificate that would be signed by root authorities. So, but yes, in the case of the code that I've shown, the scenario was you could craft a certificate with a Unicode character in the command name. So it's not possible in the out name section of the certificate, but because the subject is supporting Unicode strings, you can have this type of domain. But the big limitation, again, that is missing to have a full manual of any Java application in TLS is you would need to be able to have a sign authorities that would sign your certificate. And so far that I know, all certificate authorities have pretty strict rule at validating certificates, so it would not be possible this way. But if you are having an internal certificate authorities, this would be far-fetched but possible attacks.
Makes sense.
So, you know, but yes, it would be possible to, for example, have Facebook with a Kelvin degree as a K, and because and you would put this in a malicious certificate that is returned to the client, and because the client will compare with a prior to that a lowercase operation, then those name would match. But again, this certificate would need to be signed by some authorities. So it could be a scenario that you have somebody, maybe a country or highly motivated attacker that knows about root authorities that want to hide from the transparency log because organizations are actively monitoring certificates that are generated with their domain. So it could be a way to maybe bypass it, but it's kind of not probable. So, but yeah.
Still possible, but not probable. Right.
Yeah. There will be an article soon. As soon as the vulnerability is published, there will be more detail about it. But yeah.
Cool. On the GoSecure blog?
Yes.
We have another cute question. Somebody asks, what's your favorite Unicode code point?
I would say the most common one is K, so Kelvin, because it's working both with the normalization form canonical, so NFC, and it's also working with two lowercase because when comparison are insensitive of cases, it's in general developer will choose two lowercase, which has a bit less character available. But yeah, I would tell you, you don't need to, when you do code review, you just find the operation that is done and you look at the characters that are possible. But if you are testing blindly, I would say K is the one to start with. Yeah.
Okay, let's do one last one. To your knowledge, are such transformations included by commercial scanners such as Burp?
I don't think so, because even in code review, it's lowercase and uppercase are pretty common, but it really needs to be in security critical components. But it could actually, but it's more, we're looking mainly for logic flaws. So if you're bypassing maybe a SSRF filter, so to bypass a filter that to be able to reach specific domain or host, it's theoretically possible, but it will be limited.
Okay, well, we're out of time, a little bit late. Thank you very much, Philippe, for your presentation. It was great. Let's give a big round of applause on Twitch chat for Philippe Arteau. And we'll be back really shortly with the last presentation of the day. Stay with us, please, and peace.